This webinar will be presented by myself and Ahmed Alkashab. So we will start with a brief introduction. So my name is Ishu, and I am the Senior Modeling and Operation Engineer at the Rail and Transit in Canada for WSP. And I'm also leading the modeling and simulation team here in Canada. I came from the background of transportation engineering and industrial engineering, and I have approximately around 9 years experience, and I've been with WSP for around close to 5 years. And my areas of practice are mainly in rail operation modeling simulation, public transit operation planning, passenger flow analysis and modeling, and timetabling and capacity analysis. Over to you, Ahmed.
Thank you, Ishu. Welcome, everyone, and thank you for joining our presentation today. My name is Ahmed Alkashab, and I'm a senior systems engineer and project manager with WSP Canada here in Toronto. I'm an electrical engineer by training, and I've been working in the rail industry for over 13 years now in various capacities. I've worked in the fields of systems engineering, automatic train control, system verification and validation, on-site testing and commissioning, and otherwise other various design work for systems and communication in the rail field. In recent years, I've been mainly working within the rail modeling and simulation team alongside my partner Yishu, with a focus on modeling and simulation of both rail operations and operations in conjunction with the simulation of traction power distribution systems for load flow analysis. And that's it. Thank you.
Right. Thank you so much, Ahmed. So from this point on, we're going to turn off our camera, and we'll turn our cameras back on once we get to the Q&A session. Okay. So here is a brief agenda of what we're going to discuss during the presentation. So we're going to start with an overview of our model and simulation and our team and the projects, and then we're going to focus a bit on our case study, which is the Goryeo expansion on corridor works, and we're going to wrap up with a summary. So we would like to start with asking a fundamental question: what is modeling and simulation? What about a graph? And what about a plot, weather forecast, a 3D demonstration, aerodynamics? The official definition of modeling simulation is that it is a representation of the real world using mathematical formulations. So a spreadsheet can be modeling. Weather forecast is a simulation. A mathematical formulation describing a relationship between two variables is also modeling. Trains running on a network is simulation. And 3D demonstration is also a form of modeling. There are various types of simulations. On a macroscopic level, we use simulations for demand analysis, ridership forecast, and it focuses on overall performance using aggregated results instead of individual movements. And the indicators, the key indicators often used include density and flow rates. On a microscopic level, we use simulations to study individual movements as well as its interactions with its surrounding environment. There is also another type of simulation, which is called mesoscopic. It sits in the middle between macroscopic and a microscopic. What it does is that it simplifies the part of the model that is less critical, while it is still able to produce detailed individual movement results as a microscopic model. Looking from a project lifecycle perspective, modeling and simulation can be used in almost every major stage, from planning to design to implementation and operation and maintenance. The role of modeling simulations changes drastically during each of these stages. For example, in the planning stage, data is extremely limited, and modeling simulations can be used to validate and eliminate scenarios or design concept options that just doesn't make any sense. Where in the implementation or operation and maintenance stage, modeling simulation can work hand in hand with design and implementation team to implement an iterative design process to achieve an optimal design output and a focus on level of service the system could provide. Let me make a guess. So most of our audience today, I guess you're very familiar with clash detection from BIM, which is the Building Information Modeling. So as you might know, the key purpose is for clash detection is really to use software to detect if two or more elements in your design takes up the same space. What will happen if we don't do clash detection? Well, there is a real life example, which I found on the top 40 engineering design fail list. The consequence of not doing analysis or spending effort at an early stage is usually very pricey, especially for large scale infrastructure projects. The same could apply to railway operation projects. We do real operation simulations to evaluate if the proposed timetable would work in the real life. And if we see conflicts, we try our best to resolve and update the service plan to minimize the systematic failure from an early stage. And if we don't do it, or the analysis is not comprehensive enough, we might end up with causing delays to thousands of commuters who rely on the systems every day. And similarly, we look at passenger circulations, passenger flow at transit facilities, and detect if there is any bottleneck or choke points in design, and we catch them at an early stage and improve it. If we don't do it at an early stage, in real life, we would have overcrowded platform that even poses safety risks for any passengers or customers that rely on it. So we all know that as the project lifecycle progresses, we have less and less opportunity to change design elements, and any changes at a later stage could incur a large cost. Once design is implemented, it's almost always very costly to rectify the situation once it occurs. While the benefit of using simulation is that we're able to catch this at an early stage and come up with plans and design changes to address these issues so that we can save money as well as ensure customer safety and provide a preferred level of service the system that can offer. So at WSP, we recognize the importance of modeling and simulation, and we think by having such capabilities, it would really help us to add values to the project and help our clients be future ready. Our modeling and simulation team sits within Rail and Transit Canada. Currently, we have around 30 members across Canada to support our work, and we offer 4 main services, including rail operation simulation and analysis, traction power low flow simulation analysis, pedestrian simulations and passenger flow analysis, and last but not least, 3D modeling. I also want to point out that WSP has modeling simulation experts located across the globe with expertise and experiences in different types of transit systems, as well as various standards and applications. And we have a global network that allows us to share our point of view and experiences which might benefit the project in other regions. Throughout the years, our team had opportunities to get involved in many exciting projects. So we just list a few on this slide. For City of Edmonton, we mainly focus on its LRT systems, where we perform operation analysis and a pedestrian modeling project to some of its network and the stations. For TTC, here in Toronto, we have projects for subway lines as well as streetcars, where we performed rail operation analysis and concept operation plan development and LRT operation performance analysis, as well as this streetcar low flow study. For Metrolinx, we are heavily involved in its subway extension program, providing operational analysis, concept of operation development, and most recently, we're very proud to be part of the Unexpress team, who will be delivering the Go Rail expansion on Corridor Works project. So this is actually a very good segue where I'm going to hand over to Ahmed, who is the project manager for the WSP-TSP development team for the Encore project, to provide a bit more insight.
Thank you, Yishu. So next slide, please. Thank you. So to start, I would like to give a high-level overview of the Metrolinx on-corridor expansion project in general, and describe why this recent bid proposal project on our part was a significant example of how our team's work has been pivotal in the overall design process of major transit design projects. So from a high-level view of this project, Metrolinx, as the current owner and operator of the GO train rail system, which serves the greater Toronto and Hamilton area here in Ontario, is looking to drastically improve and expand this service over the next 24 years. And to do so, the Ontario provincial government has committed a historic investment of more than $15 billion dollars Canadian to fund this expansion of frequency and quality of GO train service. So currently, the GO train network has over 400 kilometers of track and an annual ridership of 57 million people, translating to approximately 78,000 train trips per year. And the goal is that after the Encore expansion project is completed in 2055, the network will include an additional 200 kilometers of track and will support an annual ridership of 200 million commuters. A few other key points that were advertised for this project was that there was going to be 42 stations upgraded, 687 kilometers of track electrified, 6 new maintenance and storage facilities, 14 bridge upgrades, and 11 pedestrian and river grade separations added, and a target of 29% faster train operation with a 60% lower operational cost. So to communicate this ultimate vision of the project, the Ontario provincial government clearly defined the requirements and objectives within the released RFP and companion project agreement documents, which were tendered to the public. Can you, next slide, please? And WSP partnered with several other firms in a joint venture agreement to submit a bid proposal for this landmark contract. The comprehensive bid submission package was very extensive and was required to include plans and design documents for all aspects of construction, deployment, and future operation of the proposed upgraded system. And this included, for example, architectural drawings for all stations to be upgraded, detailed track alignment drawings for all the guideway upgrades planned, traction power system design, and phasing plans for the electrification. Proposed vehicle configurations, fleet and crew rostering plans, upgraded signaling system design, and as well as a complete 48-hour timetable provided for the key years throughout the target time period of 2025 to 2056, as well as incorporating passenger flow data and much more, actually. So it's very very large and comprehensive design package to be submitted for the bid. And as you can see, all of these elements were inputs to the operational model and simulation activity that we provided for the team. So one of the key requirements was obviously to submit a compliant and design representative OpenTrack model and corresponding train service plan, consisting of timetables for the key service years I mentioned, which were 2025, 2032, and 2056. And also incorporating the fleet configuration and consideration of all third-party rail usage for freight and intercity services. So this complex and challenging bid proposal took 2 years to prepare and submit, and consisted of significant design work from multiple disciplines, and the ultimate convergence of all these designs in a comprehensive manner were incorporated in the model that we developed and submitted to the sponsor, and demonstrated that the holistic design package was feasible and compliant to all the requirements in the project agreement, and the projected performance of the proposed solution was meeting or exceeding the targets from an operation perspective. So next slide, please. So as I mentioned, our responsibility as the WSP modeling and simulation team within the bid development effort was the formation of the model, as I described, which would represent the integrated system design proposal as a whole, and we could simulate the correlated service scenarios for all the key years that we had to propose train service plans for, and would provide effective data for analysis and validation of the compliancy, feasibility, and performance. So this process, the main challenge in this process was to maintain the integrity of our model throughout the design process, regarding the accuracy represented in the model of all the design data, which was a combination of existing as-built data as well as our proposed design data. And this was crucial to meaningful evaluation of the design as a whole, and for each iteration, and crucial to providing vital feedback to the design teams throughout the process to provide any corrections that needed to be made. So generally, the proper approach to simulation of any system is made up of these steps you see here on this slide. Starting with defining your scope and objective, collecting all of the data required to build a comprehensive model, developing the base model, checking for errors, and then doing a calibration and validation exercise of the model that you produce against real-world data, ideally. Then developing and running your scenario tests, and then evaluating and analyzing the output data and providing conclusions in a final report. However, to achieve the bid development goals under the circumstances and within the aggressive timeline that we had, it was necessary to give the process a bit of a turbo boost, which was done primarily through innovation in process and tool development. Thank you, Yishu. So the output data of the industry standard software tools used for the macroscopic timetable development are not readily compatible with the input formats that we require for the microscopic simulation software that we use, OpenTrack in this case. So as a result, historically, the integration of timetables and the micro simulation operational models required a lot of manual intervention and data formatting at every step. So to mitigate this bottleneck in the process and meet the project requirements and timeline, we developed several tools, data processing tools and formatting tasks were automated, and the detailed modeling processes were developed further and refined to find any efficiencies that we could. So this slide just shows some, sorry, next slide. This slide shows some of the visual outputs that our in-house tools produced, which were extremely useful in automating the finding of connections between interlining train courses, for example, evaluating the on-time performance against the PA requirements incrementally throughout the bid development process to give us instant feedback on how the TSPs were performing, and also generating enhanced time distance plots that you can see on the right, which were vital for investigating and resolving any deadlocks or critical delays that we were seeing in our simulations of the operating plan. So that, in a nutshell, that's the application of our expertise to this project. And In addition, I wanted to highlight some of the future-ready aspects of this project, starting with the growing transit ridership demand relating to the population growth in the Greater Toronto and Hamilton area occurring now and over the next couple of decades. Our team leveraged the modeling and simulation techniques to assess the various infrastructure development concepts and propose a reliable and high frequency service plan to exceed our clients' expectations and deliver a greener solution for transportation in the region. The electrification of the network will also reduce greenhouse gas emissions and air pollution. And as a part of our service plan development, our team supported the rail network electrification concept by demonstrating the operational benefits of using electric trains, and operating high performance electric locomotives was proven to be an essential provision to the high frequency service we wanted to provide. For data management and analytics, the design development heavily relies on data collection, coordination, and stakeholder engagement. Therefore, WSP contributed to 2 areas of the infrastructure improvement and operational concept design, using ProjectWise and BIM 360 platforms to store and manage CAD drawings and design data and assign metadata to design files that streamline the multidisciplinary collaboration effort. Was very pivotal in making sure that this would be a future-ready project. And finally, the enhanced signaling technology is crucial because currently the GO train network operates on a legacy conventional fixed block signaling system that was not designed for the capacity that we are proposing in the future. Therefore, improving the signaling system with an advanced design supports the higher frequency modeled in our simulation. And the simulation again was used to optimize the location and performance of the signaling system based on the simulation outcomes in an iterative process. So this is how our project applied to being future ready. And next slide, please. So in summary, the key takeaways from our involvement in this bid proposal project is that as a modeling and simulation team, we act as a system integrator as well as perform or evaluate the performance of the design solution holistically. We produce and provide innovations through for the design process throughout. And optimize the design at every step through our simulation results and analysis. And at the end of the day, it was actually very pivotal for our winning of this contract, because it's an operationally driven concept that we're proposing, and being able to demonstrate the feasibility and compliance and performance from an operation perspective was the selling point for the client, and was a major, if not the main contributor to our ultimate win. Thank you. Next slide. So in general, modeling and simulation can be applied to multiple areas of the transit design process. As mentioned before, the 4 main areas of modeling and simulation that we apply right now is operational performance evaluation, traction power design, pedestrian flow evaluation, and 3D modeling and visualization. So value can be added at every stage of the design process through modeling and simulation. It is becoming a more recognized and required aspect of the design process in the industry as a whole, and it's good to be on the cutting edge of that trend. And this project, the Metrolinx on-corridor expansion bid, really exemplifies how we can bring the most value to a design process through operational modeling and simulation. And And that's it. Sorry, thank you. So now we'd like to open the floor to any questions that anybody may have regarding this presentation and the topic in general.
Perfect. Thank you, Ahmed and Yishu for for a fantastic presentation. Sorry, losing my voice. It will be great to see you guys if you can open the webcam, and thank you for sharing with us this impressive project. I will start with the first question. What is the process for validating your model against real world data or design inputs?
Do you want to take that issue, or do you want me to take that?
Sure, I can take that one.
Okay.
So the process of validating the simulation, what we do is usually we take the there's always the input for the simulation data, right? So you take the input from could be a manufacturer's spec sheet or somewhere, and then you put into the simulation model, and using the simulation model to produce some sort of outputs based on the parameters and then algorithms or the mechanics you have built into the simulation model, and then use that output to compare with another source of truth. So for example, it could be, again, the real world data from the train operation, or it could be like a travel time from a station to another station. It could be a journey time for pedestrians move from one key locations to another locations, and you use that data to and you can use it for either individual or aggregated. Usually it's aggregated to look at the overall performance, and use and define a certain criteria, the convergence criteria. As long as you fall into that category, and you can consider the model to be validated and reflecting the real world properly. There are a lot of different methods and ways to do that, and there's actually quite a few studies that have been out there. So if you would like, we actually would be more than happy to share with some of the approaches we have seen on through our study and through our online approaches and projects as well.
Thank you, Yishu.
Thank you. The next question is, what is the main purpose of optimal operation rail transit planning?
Well, I mean, I believe that every transit system operator wants to optimize their operation for their clients and their commuters within the system, and as well as providing a better service. It also optimizing your transit system can lower your operating cost as well as improve the longevity of your assets within the transit system, and essentially just maximize the efficiency so you get the most benefit out of your transit system for the lowest cost and effort put into it. So I think that, I mean, to me, that's the main purpose of optimizing your rail, your train service plans and your operation of a system. And to me, it's evident that that's what every client wants and what every operator wants out of their system.
Thank you. Next question is, how are the operational performance targets qualified and measured?
I can take that one. So there are quite a few performance factors we look at. So for example, for rail operations, we usually look at delays, because the performance operation, when you look at it, it's usually measured from a customer's perspective. So imagine you are passengers waiting for trains. What is the key factors you care about? It's the most obvious one is like whether the train will arrive the station on time or not. So one key performance factor will be looking at the on-time performance. And the other one, for example, the potential modeling. When you look at it, again, thinking from the customer perspective, would you be willing to go through a very crowded platform or like staircase or concourse for every single day on your way on your commuting away to your office or back to home? You definitely would not like to do that. So performance factors on that part usually is described as like level of service in terms of density of the area, and in terms of how long these density of high density areas would occur. So again, it's really depending on different cases and the different objectives. We're just listing a few, but there are quite a few others that's playing in that are at play as well.
Thank you. I will take the last question, just considering the time. What level of detail does a microscopic model and simulation consider in a typical context?
Well, I think Ishu would be the best to answer that. I'll start, and then Ishu, you can supplement my answer. In general, a micro simulation will consider almost every physical factor that you can think of to apply in the simulation. For example, in the micro simulations that we provide, we have to include vehicle characteristics. You know, there are equations to measure the wind resistance experienced by a train to properly model that into the physics of the simulation. Every element or every meter of track has to have a grade, and any curvatures properly represented in the model. You know, your as I mentioned before, in terms of the vehicle, your braking rate, acceleration rate have to be consistent with the data coming from the manufacturer or any real world measured data. You have to consider, you know, the minute details such as how long a switch time, for example, how long it takes for a switch to move from tangent to turnout. The stopping point at every platform along a system has to be properly modeled and represented in the simulation. What else? I mean, honestly, everything has to be, everything that you can get data for is in some way represented in a micro simulation to the best possible degree, I would say.
Yeah, totally agree, Ahmed, on what you just mentioned. It's really, as I mentioned, for macro simulation, it's really focused on the details, like all the data parameters as much as possible. It could be braking rates, it could be switch time, it could be accelerations, and like very detailed step by step. So for macro simulation, it's really to look at the movements for every single object or entity in the system. So if you look at a real operation perspective, it's the movement of a train. And if you look at a perspective from pedestrian modeling, it is a movement of course, a pedestrian, a person. And then if you look at from a traffic simulation perspective, it's a movement of either a bike or a car or a bus or either these kind of things. And what you really want to look at is the interactive effect among all of these objects. There are constraints in the simulation. There are variability in the simulation. Like all of things you take into consideration and look at what is the overperformance. And in the meanwhile, you try to take it as realistic as possible. So yeah, this is our answer.
Fantastic. Thank you so
as
much.
detailed as possible.
As detailed as possible. Thank you. Thank you, Ahmed and Ishu, for a fantastic presentation. Sorry, guys, we're over time a bit. Thank you, everyone, for joining this session today. We appreciate your time. Please feel free to follow up directly with the presenters via the contact details shown on the screen. And again, thank you, everyone. Have a wonderful day.